Hi, my name is James Tyrrell. I'm editor of nanotechweb.org. Today I'm with Ian Gilmore, a science fellow at the National Physical Laboratory in Teddington, home of the UK's Measurement Institute. In this interview, we're going to find out more about nanotechnology by looking at how the latest tools and analysis are helping to drive product innovation. Ian, before we take a closer look at some of the tools and services on offer, I wonder if you could tell us a bit more about NPL and its focus on nanotechnology.
Well, hello James, and first welcome to NPL. NPL has a major effort on measurements for nanotechnology to support innovation and competitiveness, as well as environment and health and safety aspects. The research at NPL is focused in 5 main areas: nanochemical, nanobio, nanoparticle, nanomaterials, and nanoelectrical, which includes quantum devices. Nanoparticles are the front-runner nanotechnology, already used for increased fuel efficiency, sunscreens, cosmetics, biocides and contrast agents for medical imaging. They're of enormous economic importance, and there are significant challenges to measure their properties, including size distribution, the shape, surface area, surface charge, and their chemical composition going from the surface down to the core of the nanoparticle, as well as their behaviour and aggregation. These measurements are important for innovation and also for the increasing requirements for environment, health and safety. There is a major international effort to improve the basic understanding of health effects of engineered nanoparticles and nanoparticles from exhaust and other anthropogenic emissions. NPL has a strong focus on meeting this measurement challenge and is well networked with the key organisations including DEFRA, the OECD, Department of Transport, Department of Health, the major international standards organisations ISO and CEN, the Technology Strategy Board, and the government coordination through the Nanotechnologies Issues Dialogue Group. Nanomaterials are key to nanotechnologies, such as fullerenes, graphene, nanotubes, nanoparticles, nanowires, multi-layered films, and nanostructured materials. The inclusion of nanoscale features in materials may confer increased mechanical strength and durability, or new properties such as electrical, optical, or magnetic. Scanning probe microscopies have been a key enabler in this area, and the development of this family of techniques, including atomic force microscopy, scanning tunneling microscopy, scanning electrochemical microscopy, scanning ion conductance microscopy, Kelvin probe microscopy, tip-enhanced Raman spectroscopy, scanning near-field optical microscopy, and techniques such as photoconductive AFM are a major focus here at NPL. Nanoelectrical systems, here the quantum and classical behaviour occurs at different length scales depending on the functionality. For harder functions such as superconductivity, the boundary exists at larger scales, whereas for softer functionality like biology, the boundary is close to the atomic scale. At NPL we have a major focus on quantum devices for quantum information processing, which involves entangled photons.
I wonder if you can tell us about some of the success stories so far and where the tools and methods fit in.
Molecular layers are very important to nanotechnology in many different types of devices. In drug delivery systems, they're very important, and in these layers you have a layer of material which is then loaded with a drug. What people need to know who are developing these devices and in the innovation side is where the drug is within those molecular layers. And quite recently there's been a major leap forward in analytical capability with the development of cluster ion beams for organic depth profiling. And what we're able to do with these is use an ion beam like this one here. This fires C60 ions at the surface, and this allows us to gently remove the layers off the surface while providing chemical maps as we go through the material, and that then produces a 3-dimensional molecular image of the material. So for instance, if we look at an arterial stent, this is a device here, you can see just at the very end of that there's a metal mesh. And when the surgeon places that in the artery, this is inflated by a little balloon. This is removed, leaving the metal mesh, the stent, in place. When body fluids start to go along that, then things like collagen can build up, starting to block the stent. So smart devices now have a polymeric layer which is loaded with a drug which tries to reduce these effects. What one needs to know is where the drug is loaded in the polymer layer to get the right therapeutic benefit, because what you don't want is have all the drug at the surface or at the interface with the metal. One needs to have a nice controlled release profile. Using this instrument here, using the C60 profiling, we can actually map out where the molecule is, the active molecule, in these 100 nanometer layers of polymer. Other examples are in the organic electronic area where, for instance, these are organic electronic devices which have been inkjet printed. These critically depend on how the device is structured with these nanolayers and the interfacial chemistry between these layers. This is important for displays as well as photovoltaic applications. And using techniques like this, we're able to map out the 3D molecular chemistry. The personal care industry is very important economically, and they were an early adopter of nanotechnologies. If you look at hair care products, skin care products, they all have molecular systems in there. And for instance, if you take hair, shampoos and conditioners, there are molecules on there which will distribute around the hair surface. There are molecules in there to try and repair damage, which can happen during bleaching of hair, for instance, and to make sure that the hair is glossy and looks like the nice kinds of products that people want to have. And it's an extremely competitive environment. So if companies can develop up their product to be better than their competitors, that has got an enormous economic leverage to them. So the use of nanotechnology devices, techniques, is very important to understand what's happening. And at MPL, along with other partners, we've been involved in using nanoanalytical techniques to look at these microfibers that are in the hair and personal care industry, such as cottons and fibers. The techniques that we use there are atomic force microscopy, so this can tell about frictional maps on the surface of hair fibers. We can see what these different coatings have in terms of their ability to slip against each other, right down at the nanoscale. We can use techniques like this secondary mass spectrometer to actually identify what the distribution of the particular chemical species are that are on the hair surface. And if you look at your shampoo bottle when you're at home, you'll see there are probably 20 to 30 different ingredients in that. And with techniques very powerful like this, we can actually localize where those individual components are. If we use techniques like X-ray photoelectron spectroscopy, we can very accurately measure the thickness of these molecular layers with about nanometer resolution on the surface of curved structures like fibers and also nanoparticles. For nanotechnologies, a major measurement challenge has been able to get more chemical information at the nanoscale. Most of the techniques that we have, such as techniques like this, as we drive down the spatial resolution, we get less and less molecular specific information. So we recognized some time ago at MPL that there was a major capability gap in this nanoscale domain. So we looked at the different possible techniques that could be used to address that. And the technique that we felt was most relevant was tip-enhanced Raman spectroscopy. This allows us to get Raman spectroscopy, which is normally limited to micron resolution because of the diffraction limit. By using a near-field method, we can take that resolution right down to about 25 nanometers. And by theoretically, we think we can get down to about 7 nanometers resolution. The beauty of this technique is we can then get Raman images of individual carbon nanotubes. We can image the nanotube, we can get the information about the functionalization of the nanotube all along its length, and we can also see if the nanotube's been filled by particles such as cobalt chloride. So this is an exquisitely powerful technique. At the moment, it's been developed to operate in ambient conditions, and in the future we're moving to be able to use this in liquid environments, and this is very important for biological applications. So this combination of nanoscale resolution in ambient and liquid environments makes tip-enhanced Raman spectroscopy a very powerful technique for now and into the future.
Ian, what kind of skills and background are useful when it comes to working with nanotechnology?
Physics underpins much of the science that we do here. At nanotechnology, it's critical to have multidisciplinary teams. We rely critically on assembling teams of people with biology, chemical, mathematics, statistics, and not just people at MPL. We have to be agile, be able to work with the best people in industry, and also use international networks by identifying what the measurement challenges are, what the industry challenges are, and then working with the best people, the best groups to really make the kind of major impact that you need to do to drive through product innovation.
MPL has links with scientists and engineers across the globe. What role do these collaborations play in your work?
International collaboration is critical to tackle these measurement grand challenges in nanotechnologies, and we collaborate with leading groups, academic and industrial groups, both in the UK and internationally. We talked a little earlier about the use of C60 ion beam was very powerful. New developments in Japan are using argon superclusters. These are starting to show great promise for being able to get these three-dimensional molecular maps from materials which hitherto haven't been possible to do using the C60 ion beam. In the US, we have a strong collaboration developing in Seattle with an NIH lab. This is Dave Kastner's lab, where they're doing bioengineering, and we're using their developments to work with our new atmospheric mass spectrometry techniques like the desorption electrospray surface ionization, because then that allows us to understand all sorts of the physics and chemistry that's happening in the interaction of the electrospray with the surface, and to really tighten that down with some very, very robust and bioengineered devices.
That's great. Thanks for sharing some of the highlights of the work here at NPL.